This particular law or this particular statement that voltage is directly proportional to current is only valid under one condition. So how exactly does a semiconductor diode behave under electric current when it is connected to a circuit? At this particular time, the temperature in this room is 28 degrees Celsius, or the room temperature is 28 degrees Celsius. Kilowatt hour is the unit of commercial use of electric power. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we will be discussing about the limitations of Ohm's law and their dependence on certain other conditions. So we were discussing about Ohm's law, which stated that the voltage in a circuit will be directly proportional to the current running through it, given that the temperature is constant. Or else we can just simply write it as V is equal to I times R, where R is the resistance. So if hypothetically we have a circuit where we have V volts of battery connected to a resistance R through which I amount of current is running, then if we plot a graph between V and I, we saw that the graph would be a straight line. So this was all discussed in the previous session. Now we are going to discuss what is the limitation in this particular theory or concept. So what exactly that means is that this particular law or this particular statement that voltage is directly proportional to current is only valid under one condition, that is at constant temperature. At constant temperature. Only if the temperature is constant, then only Ohm's law will be valid. So let's see what happens when the temperature changes for a system. Imagine that I have a graph where voltage and current are being plotted. So for some time, let's say Ohm's law is being held. Okay. But afterwards, I see that the relation between V and I are shifting. That is, after some time, I see the curve forming in the graph and then later it dipping. So why does this happen? So when I was actually studying the current relations in a circuit, I kept on increasing the current and suddenly I noticed this particular change in that circuit. So it gave some revelations to the particular topic, that is Ohm's law. It was known that Ohm's law is only true under certain conditions, after which Ohm's law won't be held. The first condition is that Ohm's law is only followed by certain conductors known as ohmic conductors. And this particular region where Ohm's law is being obeyed is known as the ohmic region. That is, this is the ohmic region where Ohm's law is completely obeyed. And after this, we can clearly see that this is no more a straight line, but rather a curved line which is dipping. So this particular region after which the Ohm's law is no more followed is known as the non-ohmic region. So in this particular graph, we can clearly see that there are two regions. One is where Ohm's law is completely obeyed under certain conditions. That is, here the temperature change isn't that drastic. But after some time, if the current value goes on increasing, then what happens is that resistance behaves like it is not more constant. That is, we have the condition that V is directly proportional to I and V is equal to IR, given that R is behaving like a constant value. But at high currents or high amounts of temperature, that is when the temperature is changing rather sporadically, then R does not actually behave as a constant value. We have to introduce higher values of R or lower values of R depending on the conditions. So after this particular region, R is no longer a constant value. That is why up to this particular region, that is up to the ohmic region, Ohm's law is held and obeyed, but after which Ohm's law is not being obeyed. So this particular region is known as ohmic region, and the region which do not obey Ohm's law is known as non-ohmic region. Okay, so what are the other type of materials which do not obey Ohm's law? This particular graph or this particular straight line is only observed for certain type of conductors or especially in conducting materials. But what if it is an insulating material, or what if it's a semiconductor material? Because we know that there are conductors, insulators, and in between there are semiconductors. They are not as conductive as conductors, but they are not as insulating as insulators. Somewhere in the middle there lies semiconductors. So how exactly does a semiconductor diode behave under electric current when it is connected to a circuit? Does it obey Ohm's law, or is it completely different? We'll just take a look at that, and then we'll discuss why that particular behavior happens. So again, I am drawing a graph with this particular point being the origin. So I am going to draw a graph with O being the origin and V against I being the axis. I am going to check whether a semiconductor or a semiconductor diode is following Ohm's law. So, but what exactly happened, it was shocking, because the graph I obtained was like this. So at very low amounts of voltages and currents, Ohm's law was being held by the semiconductor diodes. As we increase the value of current or voltage, we saw that Ohm's law is no longer being followed. So this particular semiconductor diode or any semiconductor diode won't be following Ohm's law strictly, because this is the nature under which it operates under heavy amounts of current and voltage at very low states. Let's say if I take this particular region, then yes, Ohm's law is being obeyed because it is a straight line. But as we increase the value of voltages and currents, then the semiconductor diode won't be behaving as an ohmic conductor. So we can say that there are materials which behave Ohm's law. If we take a copper wire, then we can say clearly that it is an ohmic conductor under a constant temperature. But if we take a semiconductor diode, we have to say that if the voltage and current are increasing, then we can say it is not an ohmic conductor. So there are materials which obey Ohm's law known as ohmic conductors, and there are materials which do not obey Ohm's law known as non-ohmic conductors. And this particular graph proves that semiconductor diodes are non-ohmic conductors. This particular graph is for a diode. So this particular graph is for a diode, and this proves that Ohm's law is not being obeyed for this particular diode. And we saw that for a semiconductor material also, initially it follows Ohm's law, but after some time it does not follow Ohm's law. So we can say that at low currents or low values of voltage and currents, it does follow Ohm's law, but after which there becomes a region where Ohm's law is not being followed. This is known as the negative region. So we can just simply say that there is an ohmic region where Ohm's law is followed and a non-ohmic region where Ohm's law is not being followed. I just want you to remember the nature of the graphs. For a diode, it will be like an S shape. That is, if I plot a graph, it will be like this. Now this is a V against I graph for a diode, and if I plot it for a semiconductor, the nature of the graph will be so that V against I, initially Ohm's law is being held, but after some time Ohm's law is not being applied. So this will be the nature of the graph for a semiconductor. Initially, Ohm's law is being held, but after some time, Ohm's law is not being held. So these two graphs are kind of important because they can ask you about what is the nature of a graph for a semiconducting material or for a diode. So just remember how the graphs or the nature of the graphs exactly are. Now more on to the temperature part. How is temperature actually related to these materials? But before that, we have to discuss some other property, that is resistivity. We saw that resistivity is equal to 1 by sigma, which is conductivity. Inverse of conductivity is known as resistivity. So what exactly is resistivity? Resistivity can easily be explained as the ability of a material to resist the electric current flowing through that. That is, if some electric current is trying to flow through a circuit, if that material has the ability to resist that flow, then we can say that that particular material has a high amount of resistivity, or we can just say that resistivity is nothing but resistance per unit length. R by L will be equal to rho. But this resistivity will be different for different materials. For example, if we take a conductor, the resistivity of conductors is fairly low because we know that conductors will allow electric current to pass through them. So we can say that the resistivity for conductors is in the range of 10 raised to minus 8 to 10 raised to minus 6 ohms meter. So this will be the conductivity range of conductors because it is very low. 10 raised to minus 6 means it is already in the range of millions. So we can say that conductivity of conductors are high, which means that resistivity of conductors are very low. And for insulating materials, it is comparatively very high because we know that plastic or any other insulating materials won't allow electric current to pass through them easily, which means that they have a high amount of resistance with them, which means they have a high property of resistivity lying within them. So we can say resistivity for insulators is high in the order of 10 raised to minus 2 to 10 raised to minus 4. It is not exactly 10 raised to minus 4, it can be higher than that, but we can say that in a general sense, insulators have a high amount of resistivity within them. So how is it related to temperature? Because we are dealing with temperature and resistance of a material, or Ohm's law and temperature dependence on that particular materials. So how does that even relate to this particular topic? So we just said that insulators have high amount of resistance in them, or resistivity is high for insulating materials. For example, air is an insulating material, but charges still penetrate through air. That is, we still see lightning flowing through the air. So how does this particular phenomenon happen if the conductivity of insulating materials is comparatively low? If their resistance is so high, then how can lightning strikes happen? So there is when temperature plays a huge role. So when the temperature increases, resistivity of certain materials goes down. For example, if we take air as the insulating material, if the temperature increases, what happens is that air is composed of many amounts of gases. There are argon, there is oxygen, there is hydrogen, there is nitrogen. There are many gas molecules in the atmosphere. So when the temperature goes up, these gas molecules get ionized, leading to charged particles in the atmosphere, which lays out a path for the electric current to just flow through it. So which means that if temperature increases, certain insulators can have conducting properties, which means that if temperature increases, resistivity of insulating materials can go down. So one property you must remember is that if temperature increases, then the resistivity of materials will go down for an insulating material. How this exactly happens will be discussed shortly, but just Remember this for now. And for semiconducting materials, it is clearly seen that if we add impurities to that particular material, we can increase the conductivity or resistivity of that particular material as we choose. So adding impurities to certain materials can affect their conductivity or resistivity. That will be discussed in the coming chapter, that is semiconductor electronics. But for now, remember that resistivity is dependent upon temperature. As temperature increases, insulating materials, the resistivity goes really down. So let's take 3 examples. That is for metals, for semiconductors, and finally for alloys, when two metals are combined together to make something new. That is, for example, the wires we use in labs or in many other industrial places is a mix of several metals. For example, nickel and chromium is brought together to make a new material known as nichrome. Like that, alloys can be made. For example, the alloy wheels of cars is a good example where different alloys are brought together and made a new material. So, let's say for alloys. So first, I'm going to consider the graph between the resistivity and temperature relation. That is, what happens to resistivity if I increase temperature for metals, let's say for copper or for aluminum. We know that if we increase temperature for a particular material, then the resistivity of that material or resistance of that particular material goes up to infinity. That is clearly seen in light bulbs. That is, we have that yellow incandescent bulbs. We can clearly see that the resistivity or resistance of that particular bulb is very high. We use tungsten in that bulb so that when we increase the current flow, that is, when we increase the temperature in that particular system, resistance increases, which means that is why the bulb glows extremely red. The heater also, the heater you use at your homes, when we increase the current, temperature automatically goes up. So as the temperature goes up, that particular material starts to glow red hot, even yellow maybe. That is because resistance is going up. So if resistance is going up with temperature, we'll get a graph like this. So this will actually go on increasing. So we can say that for metals, as temperature increases, the resistivity of that particular material also increases. And we can say mathematically it will increase exponentially to infinity. That is just a mathematical saying, but yeah, sure. As temperature increases, for metal, the resistance or resistivity will also increase exponentially. But what about for semiconducting materials? Will there also be an exponential increase? Not exactly, because we saw that innately at first semiconductors will have high amount of resistance compared to a metal because they are obviously lying in between insulators and conductors, which means that resistance of semiconductors will be comparatively high in the initial stage. But as I increase the temperature, it was clearly seen that the resistance actually dropped along with increase in temperature. That is, resistance rho decreased as I increased temperature. Now, why would that happen? For metals, it went exponentially up. Why? Because as temperature increases, resistance went up. But why would semiconductors behave differently? That will be explained very shortly. But there is one more material who is behaving quite sporadically. That is alloys. So, if I plot a graph between the resistivity and temperature of an alloy, that is, let's say for nichrome, it was seen that the graph is almost a flat line. There is a slight incline, but other than that, it is almost a flat line, meaning that the resistivity and temperature factor is almost independent for an alloy like nichrome. That is because these particular metals does not depend, or the resistivity of these particular metals or alloys, resistivity of certain alloys do not depend much on temperature, but it slightly is depending on temperature. That is why there is a slight incline, but other than that, it is almost independent. So there is not much of a sporadic increase or decrease. So it is almost flatlining. So we can say that temperature dependence of alloys is comparatively less. That is, resistance and temperature is not too dependent in the case of alloys. But for a metal and semiconductor, it is highly dependent. That is, for resistivity is going down in a semiconductor while resistivity is going infinitely up in a metal or conductors. So why does this particular behavior occur? So that will be discussed right now. The temperature dependence on resistivity is actually given by this particular equation, which states that this is the relation laid out by great scientists, forming the relation between resistance and temperature. I know it is kind of out of the blue, but this is a relation between resistance and temperature given in your textbook. So actually it can also be written in the form of resistance, because there are questions being asked in terms of resistance also. So we can actually write it in terms of resistance also. So this states that rho t or R of t is nothing but the resistivity of a material at a given temperature. So if initially, let's say I have a light bulb at room temperature, so that room temperature is the reference temperature, and that is indicated by TO, or the resistivity at reference temperature, rho naught. So rho naught is known as resistivity at reference temperature. For example, if I'm taking the reference temperature as room temperature, then I can say it is 300 Kelvin or 28 degrees Celsius. That will be the reference temperature, the starting stage where rho naught has a fixed value. That particular temperature in the reference condition is known as T naught. And T naught is the reference temperature. Let's say, for example, 28 degrees Celsius. That is, I'm saying that I have a particular wire which is going to be connected to a circuit. When I'm connecting this to the circuit and just starting the experiment, I note that at this particular time, the temperature in this room is 28 degrees Celsius, or the room temperature is 28 degrees Celsius. That is the reference temperature. And the resistivity of material of this particular wire or anything you're taking is the resistivity at reference temperature. That is, the resistivity of the material of the wire measured at room temperature or at reference temperature is known as resistivity at reference temperature. And as you begin the experiment, as you go on with the experiment, more current is flowing through this material, and this particular material has resistance, so it gets heated up. The temperature in this system changes. That particular temperature is the temperature indicated by capital T. The temperature of the material once you have started the experiment, and the change in temperature is noted down. So the new temperature is T. Rho T is the resistivity at this new particular temperature. Rho T is the new resistivity at temperature T. Now there is one more factor known as alpha. This particular alpha is known as a constant which has a fixed value for different materials, and that particular alpha is known as coefficient of resistivity for temperature, or alpha is temperature coefficient of resistivity. It's a mathematical quantity which will have different values depending on the different type of material you're using. So this particular equation, that is, this particular equation gives you the relation between resistivity and temperature of a material. If, let's say, you're starting an experiment with a new material, let's say a copper wire, you're connecting it to a circuit and you're passing current through that particular circuit, then you can say that at initial conditions, this particular circuit, let's say this is the circuit. As you're just starting the experiment, the room temperature is noted down as T0, and this particular copper wire will have a resistivity of, let's say, 5 ohm meters, for example. Not 5 ohm meters actually, but let's say it is 5 ohm meters. So that will be rho naught, the reference resistivity. And after you started the experiment, that is, I'm connecting the end, shorting the circuit, then the experiment began, current is flowing through this particular circuit, and automatically the temperature goes up, and that particular temperature is capital T, and the resistivity at that particular temperature is known as rho T. So that is, that particular relation is connected using this particular equation, and alpha is the temperature coefficient of resistivity. Just note it down. So why this happens is because we know that resistivity is equal to 1 by sigma, 1 by conductivity, and the equation to find out conductivity is that N E square 2 divided by M. So this is the equation to find out conductivity, which means that the equation for resistivity is nothing but M divided by N E square 2, which means that resistivity is inversely proportional to the relaxation time tau. If you remember the graph for the metals and semiconducting material, we can clearly see a relation forming. That is, let's say this is the particular circuit for which I have connected the semiconducting material or the metal through which a current is passing. Now we saw that in the case of drift velocity, that electrons will be experiencing a force and they will be traveling. Vd was directly proportional to tau and inversely proportional to the temperature. So we can say that right here, resistivity is inversely proportional to tau, which means that as temperature increases, as temperature is given into the system, if current is flowing through that, because of resistivity and resistance, the temperature of this particular system is going to increase. As current is flowing through that particular system, temperature in that system is going to increase. This particular temperature is going to be accumulated in the electrons. It is going to be absorbed by the electrons, which means the electrons in this system is going to get some energy, which means that the collisions will happen much more faster, which means that the relaxation time will decrease. So as the relaxation time decreases, the drift velocity increases, which means that there is a dip in relaxation time, which means resistivity will go up. So that is why in the case of a light bulb, that incandescent yellow bulb, as you pass electricity through that, as the material, the tungsten material gets heated up, more electron collisions occur and the resistance of that particular bulb, the resistivity of that particular material will go up. That is why for metals, we have the graph increasing exponentially. That is because this particular relation, that is rho, is directly proportional to 1 by tau. So if the relaxation time goes down, then resistivity will go up. Note that here N, that is number of free electrons, is not increasing or decreasing. For a metal, that is for a conducting material, the number of free electrons available won't be changing. But the relaxation time will be changing because heat is applied to that system. As current is passing through that system, because of resistance, automatically it will get heated up, like in the case of a light bulb or a heating material, heating coil, anything. So as heat is supplied to that system, these electrons will absorb that particular heat being supplied and they will move even faster, meaning that the collisions will be happening frequently, which means that resistivity will be going up because they are inversely related. So as torque decreases, resistivity increases. That is for metals. Now what about semiconducting materials? Here we have to take one more thing into consideration. That is, rho is also inversely proportional to 1 by n. So if you remember the derivation of drift velocity, we know that n is the number of free electrons per unit volume. So if temperature is increasing for a semiconducting or insulating material, this particular n value changes. That is, as we took the example of air, when air was heated up as the insulating material, more and more charged particles were available. That is, the nitrogen gas, the argon gas, all those gases heated up, releasing ions into the atmosphere, paving a path for the lightning to come through. Just like that, if resistivity increases, the number of free electrons available also increases. So this increase is enough to counteract any small increase in relaxation time. That is, even though tau is decreasing, the increase in number of electrons per unit volume for semiconducting or insulating materials is more than enough to compensate for the small increase in tau. That is, to be more clear, we saw that this was the graph for semiconducting material. That is because even though this relation exists, that is, rho against T is increasing because relaxation time is decreasing. But for metals or conducting materials, N was not changing. Here, for semiconducting materials or insulating materials, the number of free electrons being available is changing. It is increasing right now. So this increase is enough to counteract any decrease in the tau value because it is comparatively very low. And the number of free electrons available is increasing. So we can just say that this particular relation is because for a semiconducting or insulating material, as temperature increases, more and more free electrons are being available, which means that the resistivity will decrease. As more number of free electrons are available, conductivity is the factor that is going to increase, which means that the inverse of that, resistivity, is going to decrease. So that is the reason why we have a graph like this one. I hope you have understood this one, because we are moving down to a new topic, that is electrical power. So what exactly is power? So imagine that I have a Lamborghini or a Ferrari. Let's say I have a Ferrari. And my friend has, let's say, an Innova. So let's say my friend Vishnu has an Innova, and both of us are really good friends, but I'll travel alone in my Ferrari while he goes with his family. So we are both going to, let's say, Bangalore. So imagine that I reach Bangalore from Mysore. Both of us are starting from Mysore. So imagine that I reached Bangalore in 2 hours. And imagine that my friend Vishnu is going to reach in his Innova into Bangalore at the same location in, let's say, 4 hours. Okay, so why is the difference in time here? Both of us are traveling in the same route. We are both going at the same time. We are starting at the same time, but we are reaching at a different time. That is because you can say that one of us went even faster. So what factor allowed me to go faster? It's very obvious that it is the Ferrari's higher power engine. So I have a powerful engine and he has a less powerful engine, which means I got to Bangalore faster. So let's look at this from a physics standpoint of view. So I did a work. I traveled a distance. I'm doing a work. Let's say I have done a work faster compared to another person, which means I took less time to complete a work compared to my friend Vishnu here. So I can say that I did it because of a powerful engine, which means power is the factor here. So to calculate power, we can use the equation power is equal to work divided by time. That is, I did a work that is going to Bangalore in my car. I did that work in 2 hours. But Vishnu took 4 hours to complete that particular work, which means that here I am doing a work in less amount of time. I have more power. which means my car has a higher power. But Innova is doing that particular work in a longer time, which means that his particular power is less compared to mine. So that is the factor you have to remember here. Work done by time is power. That is very simple. Now we are going to study this in terms of electric current, and we are going to relate this to Ohm's law. So how can you relate work with charges? So we know that the definition of V, that is potential, is given by the equation work divided by charge. Or the definition of potential is that the work done in bringing unit charge or work done per unit charge is known as potential. So we have an equation that is V times Q is equal to W. We have an equation in terms of charges and potential which relates work. But we also know that the equation for power is work divided by time. That is, P is equal to W by T. That is also clear. So right now we have an equation for work in terms of charges and potential, VQ, and we have an opportunity to substitute that particular equation into the equation for power, so that we can write this particular equation as V into Q divided by T. Now, if you remember the definition of electric current, that is the flow of charges per unit time, that is I is equal to Q divided by T. So we can say that Q by T is nothing but I. So we have a Q and a T here. So combining these two things, I can write the P is equal to VI. That is, power is equal to voltage times current. So if I am talking in terms of current and voltages, that is, if I am saying that I have connected an electric bulb to a circuit, then I can say at what power that particular bulb is operating. Or let's say this is a motor. Let's say this is a motor pumping. This is a motor pumping water. So I can say how much voltage, how much current it requires to work at a certain power level. Let's say 5 horsepower, so that this particular motor can work efficiently. So in order to calculate the power required for that particular circuit, I can use the relation between voltage and current. We are not exactly done here. We have to relate this to Ohm's law also. So we just figured out that P is equal to W by T, which is equal to VQ divided by T, which is equal to VI. So this is the equation. Now we have P is equal to VI, but we know that according to Ohm's law, V is equal to IR. So I'm going to substitute this IR in this equation for V. So I can say that this particular equation can be written down as I into I times R. That is, V is equal to IR. So we have an I here, and instead of V, I'm going to write IR, which means that I'll get the equation as I square R. Now, why would I just do that for just I? Because I have a V here also, right? So I'm going to rewrite this equation as V by R is equal to I. We can write this particular equation again in the form of V into V by R. So this can be written as V square by R. So now we have 3 equations in terms of power. That is, P is equal to VI, that is 1. P is equal to I square R, that is 2. P is equal to V square by R, that is 3. We have 3 equations dealing in terms of power. This is very important because all the numericals in this chapter can be asked through a question relating power. So this is very important. Please note this down. One more important thing is that the unit of power. We can say that the unit of power, P is equal to W by T, can be written as joules per second, But since we are paying tribute to many scientists who have worked on many countless topics, this particular power is being named after a particular scientist known as watts. So the unit of power is capital W, that is watts. So it is, you can either call it joules per second or you can even say watts, that is the unit of power. Generally we will say in terms of watts, that is how much watts a car have. Let's say you have an electrical car, then you can say that that particular electric car has a capability of 1000 or 600 kilowatt. So we can say it in terms of watts. Now for commercial use, that is for commercial use, we don't use watts because watts is very less. When we power an electric bulb or an electric toaster, we use watts. But when we are doing it for houses or like industries or cars, we don't have enough watts. So we say it in terms of kilowatts. So we use kilowatts, kW. And time is also a factor here. So how much time are you using this particular power for? For example, in your household, the electricity is being recorded down in your meter in terms of kilowatt hour. So how much time are you using this much power for? So we can say kilowatt hour is the unit of commercial use of electric power. So this particular kilowatt hour can be written down in terms of joules also. So if you're writing down in terms of joules, we can say that kilowatt hour can be written as, how much is kilo? 10 raised to 3, that is 1000. And W is watts, and hour. 1 hour is 3600 seconds. 60 seconds into 60 minutes will give you 1 hour. So we can write it as, so this will become 10 raised to 3 into watts into 60 into 60, that is 3600. So we have 2 zeros here and 3 zeros here. So we total have 5 zeros. So just to write it in terms of one numerical, I am going to write it as 1 kWh will be equal to 3.6 into 10 raised to 6 joules. This is kilowatt expressed in terms of joules. So it is 3.6 into 10 raised to 6. That is, you have 3 zeros here, 2 zeros here. So total 5 zeros. So it will be 36 into 10 raised to 5 joules. But 36 is a big number. So I reduced it even further, just saying 3.6 into 10 raised to 6 joules. So 1 kilowatt hour is this much energy. And if you're seeing it in terms of horsepower, if you have an electrical car, you want to compare that, how much bhp is that particular car having? So we can say that 1 HP or 1 bhp is equal to 746 watts. 746 watts. So these are just two things you can remember if the question is given in a different form. That is, instead of asking for kilowatts, your question represents that your household consumes, let's say 10 into 3.6 into 10 raised to 6 joules of energy. Then don't be alarmed. 3.6 into 10 raised to 6 joules is nothing but 1 kilowatt hour. Given in terms of horsepower, you should also not be confused because horsepower also can be converted into watts. So this is the relation between power and our chapter, that is current, electricity. So I hope you have understood about power, electric current, and the relation between temperature and Ohm's law. So I'll see you all in the next class with a new topic. Until then, take care. Thank you.